let's try to solve this question here. You have a battery of EMF epsilon and internal resistance of small r is connected across a variable resistor. Okay, so if you would like to imagine it, a simple circuit of it will be a battery with internal resistance. So we can draw a battery with internal resistance. So we'll enclose this inside a dotted rectangle to show that this is inside a battery. So we label this as epsilon and we label this as R. Okay, for a battery, the epsilon and the internal resistance will not be affected by what we connected outside the battery. Even if you connect it to a large resistance or you connect it to a small resistance, it will not affect the electromotive force and also the internal resistance of the battery. Okay, it is unaffected by anything that we connect outside the battery. So these two things should be constant, even though if we vary the resistance of the resistor that we connected to. Okay, so we can connect it outside. There's another resistance, but this resistor is a bit different. This is a variable resistor, so you are able to adjust the value R over here. Okay, so they are going to set it in two different situations. When the resistor is set to 21 ohms, so right now R will be equals to 21, then they find that the current through the wire is 0.48 ampere. Okay, so let me modify a bit the diagram to put in an ammeter just to show the situation clearly. Okay, so I'm going to install an ammeter over here connected in series, and they give me two different situations. The first situation is if I set my R to be equals to 21 ohm, and at that moment my I is equals to 0.48 ampere. So that's the first situation that I set myself to be in. Okay, then the second situation is when I set it to be at 36 ohm, means I change this resistor to 36 ohms. The current through is 0.30 ampere, so the current over here will be changed to 0.30 ampere. Okay, so let's write it down as well. Second situation, maybe you can call it as R prime to represent a new situation. So R prime is 36 ohm, and when we say it's 36 ohm, we read the reading of current. The current reading of ammeter shows that it's 0.30 ampere. So we have two different situations over here, but even if we change the variable resistor over here from 21 ohm to 36 ohm, again, like what I said just now, the electromotive force and also the internal resistance will not be affected by what we change outside the battery. Okay, these two things should be constant. Of course, you can think that, oh, if I use the battery for quite some time, after 2 months later, it might the amount of energy left in the battery might be depleted already. In that case, electromotive force might change or the internal resistance might change. That's another issue. Okay, yes, the EMF may change if you use the battery for quite some time. But what I'm talking about is, if you connect it to a large resistor or you connect it to a small resistor, what kind of resistance that you connect it to, it won't make any changes to the electric motive force. It won't make any changes to the internal resistance. Okay, it is you cannot influence the electromotive force or the internal resistance by doing something to the external circuit. You cannot do it like that. Okay, you can only deplete the energy of the battery, then it's another issue. Okay, so let's write down the two equations. The basic idea of an electromotive force, you can think that this is the energy supplied by the battery, okay, per 1 coulomb of charge. Okay, energy supplied by the battery, then the energy itself is being used, a portion of it is being used by the battery itself because we want to get through the material of the battery, and the portion that is left will be given to the external circuit. So this is the one that will be given to the external circuit, or we call it as the terminal voltage. Okay, so it's important to be clear what is terminal voltage. Okay, terminal voltage is the voltage that you can read if you connect your voltmeter to the two ends of the battery terminal. Okay, in other words, right, this voltage that you read is also the energy that can be supplied by every 1 coulomb of charge to the external circuit. Okay, because what we can measure is what is available for the external circuit. Okay, these two here, they will be the you can think of it as the voltage used by the material, used to get through the material of the battery. Okay, so energy used by every 1 coulomb of charge to get through the battery. Okay, it's wasted, okay, to get through the battery. Okay, so this energy will be used inside the battery, then what's left will be used outside the battery. Okay, so if you combine these two, this is energy used inside the battery, this is energy used outside the battery. If you combine them, there's a total amount of energy that the charge received from the battery. So that's the idea of electromotive force. Okay, so this is electromotive force, EMF. Okay, of course I can change this equation to be epsilon is equals to IR, and I can change my terminal voltage because terminal voltage still follow Ohm's law. So V is equals to IR, but it has to be all the resistance outside the battery. So it's not just a simple IR, this should be R effective. Okay, effective resistance of what's available connected outside our battery. Okay, so if you change the equation a little bit, factorize out the current, it will be IR plus R effective. Okay, so this is the equation that we'll be using. Why? Because we know that our epsilon and our internal resistance will be constant. Whereas this one, we have situation 1, situation 2. Our R effective, we also have situation 1, situation 2. Okay, so the situation 1, situation 2, let's write down the equation. The equation 1 will be epsilon is an unknown. The current is 0.48. The internal resistance is unsure. We are not sure about internal resistance, but the effective resistance will be 21. So this is our first equation. Our second equation will be 0.30 for the current, and the effective resistance is 36. So we have two equations here with two unknown. You can just put it into a calculator, solve for a simultaneous equation. Okay, we don't need to see a working. How do you get EMF and how do you get internal resistance? That part can be solved easily by a calculator. But by solving using a calculator, I'll just write down the final answer. We can get our EMF to be equals to, our EMF will be equals to 12 volt, and our internal resistance will be equals to 4. Okay, the working is not required. But you need to display these two equations very clearly. Okay, display these two equations, and from there it's just simultaneous equation, and that part you can give it to the calculator to do it. You just need to write down the final answer, which is the EMF 12 volt and also internal resistance 4 ohm. Okay, so we can see that no matter you connect it to a 21 ohm resistor or 36 ohm resistor, the EMF is still 12 volt. It will not change. Okay, in fact, EMF, right, is what usually written on the package of the battery. If you happens to be having a 12 any kind of battery, let's say you're having this kind of battery, okay, you can read on the label, right, they probably write 9 volt or something. So that 9 volt itself is the electromotive force. And I think you can sort of think that if you connect it to a big resistance or you connect it to a small resistance, the packaging, the value 9 volt that is written on the battery won't be changed to another bigger value or smaller value, right? So that means that the electromotive force will not change. Okay, so the electromotive force and the internal resistance does not change based on what you connected outside. Okay, it's independent of what you connected outside the battery. Okay, what you change here is actually changing the effective resistance, causing the current flowing through the circuit to be changed as well. Okay, so that's it for this question. Thank you very much.